Every time you learn a skill or form a memory, your brain changes its physical wiring. For that memory to stick, specific synapses between your neurons have to grow stronger and physically bulk up to carry more signal. The biological trigger relies on specific gates called NMDA receptors. When an electrical signal hits, these gates pop open, allowing calcium ions to rush inside. That flood of calcium is the exact messenger telling the neuron to learn. But this creates a serious mechanical problem. If a neuron continuously strengthens its connections, those gates let in more and more calcium. Unchecked, that calcium reaches toxic levels, short-circuiting the cell and triggering chaotic seizures. The cell could protect itself by universally weakening all of its synapses to restrict the calcium flow, but if the gates stay shut, the network goes dark. The signals fade, and learning stops entirely. For decades, neuroscientists recognized this paradox. They observed that the brain maintained a general homeostasis to keep neurons alive while they processed new information, but the exact mathematical rules governing that tightrope walk remained invisible. Understanding how a single cell navigates the space between fatal overload and total silence reveals how the brain stores information without destroying itself. To find those rules, a team of researchers at MIT designed highly isolated experiments to observe this balancing act live at the microscopic level. They used a novel methodology known as high-precision iontophoresis. This allowed the researchers to shoot exact microscopic drops of glutamate, the brain's chemical trigger, at a highly localized 1 to 2 micron spot on a single dendrite over several hours. The team first artificially suppressed the NMDA receptors. By reducing glycine in the surrounding fluid, they made it difficult for gates to open, but the neuron fought back. Sensing the calcium drop, the cell rapidly built more functional receptors to make up the difference. The cell effectively detects external suppression and adjusts its own sensitivity to ensure its baseline electrical intake remains stable. Next, the researchers tested the opposite extreme, drastically increasing the frequency of incoming signals to hit the cell with a rapid barrage. The bombarded neuron responded in reverse, aggressively stripping away its own receptor gates from the membrane to protect the interior from calcium flooding. The researchers proved that intracellular calcium was the messenger behind this response. When they introduced BAPTA, a chemical that absorbs calcium inside the cell, the entire compensation process halted. Regardless of the incoming signal frequency, the receptor density stayed constant. They also mapped the spatial limits of this reaction. Stripping away receptors in one heavily stimulated spot didn't affect the rest of the neuron. The regulation is hyperlocal, restricted to tiny neighborhoods along the dendrite branch only 40 to 50 microns wide. A single neuron does not rely on one master volume knob to control its state. It manages thousands of independent thermostats, each adjusting its own local electrical climate. The true scale of this biological engineering emerged when the MIT team plotted all the frequency and perturbation data together to look for a mathematical pattern. This chart plots the relationship between a cell's average synaptic input and its functional receptor density. The result is a highly predictable curve defined by the inverse squared law. A staggering 90% of the variance in a neuron's receptor density is explained by this single mathematical slope. By scaling its receptors exactly to this inverse curve, the cell perfectly conserves the integral of the NMDA flux over time. If the input rate is cut in half, the cell quadruples the receptor sensitivity. The math ensures the average charge transfer never changes. The MIT researchers termed this exact accounting mechanism NMDA normalization. The brain is actively performing an ongoing calculus, dynamically tuning thousands of individual synapses to perfectly balance its electrical ledger over long periods of time. This mathematical rule creates a unique state for a quiet neuron. When a local dendritic neighborhood experiences low activity, normalization forces it to heavily upregulate, building a massive hidden reserve of receptors just to reach its required average electrical charge. That quiet, sensitized neighborhood is now a coiled spring. Then, a sudden, powerful burst of synaptic input, a distinct learning event, arrives at the dendrite. The massive reserve of receptors catches the signal all at once. Because gate density is so high, the burst generates a disproportionately massive calcium spike. That specific spike in calcium is the exact biological trigger required to forge rapid, permanent memories. By strictly balancing its electrical ledger in the background, the neuron protects its own circuitry, while ensuring that even its quietest branches are sensitized enough to trigger a permanent memory from a single burst of activity.